Hello everyone, I'm Michael Berkovich, a consultant specializing in agrochemical formulations with more than 3 decades of experience in this field, most recently as the head of fungicide R&D at Edama, part of the Syngenta group. Today I'd like to talk with you about one of the very challenging issues in pesticide formulations, the phenomenon of colorization in pesticide molecules. Many pesticides, like organic dyes, possess chromophore structures, causing them to behave like dyes. Like dyes, these molecules often face the challenge of color instability in formulations. Such instability not only affects the appearance, but also can cause performance and shelf life issues. We'll discuss the mechanisms behind this phenomenon and, based on that understanding, offer practical strategies for stabilizing color in sensitive formulations. So let's start. Mechanism of color visualization. To understand how we perceive the color of a substance, we need to consider the interaction between light, the substance, and our eyes. Light, whether from the sun or an artificial source, contains all visible wavelengths. When light hits a substance, certain wavelengths are absorbed based on its molecular structure. The wavelengths that are not absorbed are reflected, and these are what our eyes detect. Our brain interprets this reflected light as a color, which is a complementary to the absorbed wavelengths. For example, if a substance absorbs blue light, approximately 435-490 nanometers, it reflects a complementary yellow-orange color, so we perceive it as yellow-orange. In the table below, you can see the complementary visible colors that correspond to the wavelengths of the absorbed light. In this column, you see absorbed light colors. Here, absorbed light wavelengths corresponded to absorbed light colors, and here you see complementary visible color. So if a substance absorbs blue light, we see it as orange-yellow. A role of chromophore groups in determining color. Chromophore groups are specific structural components within molecules that are responsible for their color. Let's explore how they determine the color of a substance. First, chromophores are atoms or groups of atoms within a molecule that absorb light at particular wavelengths in the visible spectrum, typically between 380 and 750 nanometers. Several common chromophores play a key role in this process. The AZ group absorbs visible light and produces vivid, intense colors. The carbonyl group, present in ketones and aldehydes, is responsible for UV absorption. The nitro group is commonly seen in yellow substances. Benzene rings and other aromatic systems with their conjugated pi electron systems absorb UV light and contribute to the color seen in substances. The presence and arrangement of chromophores within a molecule structure dictate how molecules interact with light, ultimately determining the color we see. Environmental factors such as pH, solvents, and temperature can affect how chromophores interact with light, potentially altering the observed color. Let's talk now about conjugated systems and how they determine the color of substances. To begin with, a conjugated system is a specific molecular structure that directly affects a molecule's color. So what exactly is it and how does it work? A conjugated system consists of alternating single and multiple bonds, usually double bonds. This unique arrangement allows electrons to spread out or delocalize across the entire structure. Structurally, conjugated systems often have alternating single and double bonds, single bonds next to lone pairs of electrons, and quite often aromatic rings. The electrons in these alternating bonds overlap, creating what's called a delocalized pi-electron system. This system determines how the molecule interacts with light. Conjugated systems absorb light at specific wavelengths within the visible spectrum. Longer conjugated systems absorb longer wavelengths, which can make the substance appear red or blue. Shorter systems absorb shorter wavelengths, resulting in yellow or green appearances. The intensity of the color also depends on how extensive the conjugation is. The more extensive the system, the stronger the absorption of light, leading to more intense colors. Interaction between chromophore groups and conjugated systems in color phenomena. Chromophore groups and conjugated systems work together to create color at the molecular level. Chromophores act as electron-rich centers, while conjugated systems allow for electron delocalization. This combination enables electron transitions when the molecule interacts with light. The specific interplay between chromophores and conjugated systems determines which wavelengths of light are absorbed and which are reflected or transmitted, ultimately producing the color we see. When you look at the structures of pesticide molecules, always listed in tables of pesticide mode of action, you'll notice that herbicides, fungicides, and insecticides frequently contain chromophore groups and conjugated double bond systems. These are the same elements responsible for the vibrant colors we see in many dyes. Because of this structural similarity, pesticides interact with light in much the same way as dyes, absorbing and reflecting specific wavelengths to create their distinctive colors. As a result, like organic dyes, pesticides are also susceptible to color changes when exposed to environmental factors such as pH shifts, light, high temperature, or oxidation. Please take a look at the structures of herbicide molecules shown in the herbicides mode of action table. Yes, you see a lot of molecular structures containing chromophore groups and conjugated double bond systems. Now please take a look at the structures of fungicide molecules shown in the fungicides mode of action table. A similar situation can be observed with many molecules that can share structural similarities with dyes, including chromophore groups and conjugated double bond systems. And now let's look at the molecular structures in the table of insecticide mode of action. We see a similar pattern. Many insecticide molecules, like herbicides and fungicides, contain chromophore groups and conjugated double bond systems. This shared structure across all three tables shows that many pesticides interact with light in the same way as dyes, absorbing and reflecting specific wavelengths to create their characteristic colors. Deprotonation mechanism of color change. Let's explore how the mechanism of color change works when the pH changes. Adding or removing protons when pH changes affects the electron distribution in the chromophore, altering its conjugation and shifting the wavelengths of absorbed light. This process is common in pH indicators, where protonation or deprotonation of chromophore groups leads to color changes. Let's take, for example, the deprotonation of the molecule of organic dye MY5. In the figure, you can see how deprotonation affects chromophores in this molecule by altering their electron structures. The dye's neutral acyl hydrazone molecule contains two chromophore groups, highlighted by green and blue circles. Initially, a proton is attached to the nitrogen in the hydrazone group. When deprotonation occurs in alkaline medium, the proton is removed, causing electron redistribution. With the proton gone, a lone pair of electrons is left on the nitrogen, creating a negative charge and increasing the electron density along the conjugated system. Two potential electron shifts can occur. Arrows show the redistribution of electrons in these cases. Arrow 1 shows the movement of an electron pair from the nitrogen to a nearby nitrogen atom, indicating a shift in electron density. Arrow 2 shows the movement of an electron pair from the nitrogen to a neighboring carbon atom, representing another shift in electron density. This redistribution creates two coexisting resonance forms, form 1 and form 2. Resonance form 1. The negative charge delocalizes toward the nitro group, affecting the chromophore highlighted in green, while the blue circled chromophore remains unchanged. Resonance structure 2. The negative charge extends into the carbonyl group, fully conjugating the molecule. This change is seen in the blue highlighted chromophore, while the green circled one stays unchanged. See this. To summarize, deprotonation shifts electron density, forming two coexisting resonance structures. These shifts alter the light absorption, leading to a color change. Example of deprotonation in the herbicide chromophore molecule dicamba. Let's look now at how the color of the herbicide dicamba depends on pH of the formulation. The figure shows how protonation and deprotonation affects its chromophore. Protonated form. In acidic conditions, pH below 7, the carboxylic group retains its proton. In this form, dicamba absorbs light in the UV range, 230 to 180 nanometer, and appears white. Deprotonated form. In alkaline conditions, pH above 7, the carboxylic group loses proton, becoming a negatively charged carboxylite. This extends the conjugation and shifts the light absorption to longer wavelengths, making the molecule appear yellow. Dicamba formulations are available in acidic form as GR, SC, and SL, and in deprotonated salt forms with a pH above 7, like dicamba dimethylammonium, dicamba potassium, or dicamba sodium in SL formulations. In alkaline conditions, the herbicide appears yellow, while in acidic form it's white. At near neutral pH about 7, even slight pH changes can cause noticeable formulation color shift. In summary, these examples of chromophore molecules show how deprotonation greatly affects the way electrons are distributed within the molecule. This change in conjugation shifts the light absorption spectrum, causing noticeable color changes. We see this in the pH-dependent transformations of pesticide molecules that contain chromophores. Now let's talk about color instability in pesticide formulations. Color changes in chromophore molecules happen when the electronic structure shifts, altering how light is absorbed and reflected. These changes aren't just caused by protonation or deprotonation. Other factors in different formulations can also trigger them. Conjugation changes. When electron delocalization extends, the absorption shifts to longer wavelengths. It's called a red shift, intensifying the color like going from yellow to red. If delocalization shortens, absorption shifts to shorter wavelengths, a blue shift, resulting in lighter colors. This is often seen in water-based formulations. pH changes we already discussed. Chromophores with acidic or basic groups change their protonation state when the pH varies, altering electron distribution and shifting absorption. This happens often in water-based formulations where pH changes can affect color. Solvent effects. The polarity of the solvent changes the chromophore's environment, which can affect absorption, a process called solvatochromism. This is common in EC, CS, and OD formulations. Additionally, residuals of solvents from the synthesis of active ingredient can intensify color changes, especially with temperature fluctuations. Metal complexation. When chromophores bind to metal ions, they form complexes that alter their electron configuration and absorption properties, leading to color changes. This can also affect solubility, causing instability in formulations with ion-rich active ingredients or inerts. Light exposure and redox reactions. Exposure to UV light or redox reactions can excite chromophores or change their structure, causing shifts in absorption and leading to color changes. In some cases, this may degrade sensitive pesticides, affecting the active ingredient and compromising the stability of the formulation. In summary, while changes in conjugation, pH, and solvents can shift color without affecting performance, metal complexation and exposure to UV or redox reactions can lead to degradation, reducing the active ingredients concentration and impacting formulation stability. Monitoring these factors in different formulations is crucial to ensure product efficacy. As you can see in this table, trifluoralin, a dinitronylene compound, in its neutral form, gives a yellow-orange color to its EC and GR formulations. However, when it gets protonated and mixes with other active ingredients or with polar solvents, its absorption spectrum shifts, changing the color to orange-red. Fluoxenem and pendimethalin, both also dinitronylene compounds, have classic chromophore structures, like those found in organic dyes. In aqueous SC formulations, fluoxenem shifts from yellow at pH below 7 to red at pH above 7. Pendimethalin typically appears orange or yellow, but in acidic conditions, pH below 5, it turns redder, and in strongly alkaline conditions, pH above 9, it becomes more yellow. In this table, you can see that like dicamba, both imazamox and fomisafen are formulated in protonated and deprotonated forms, such as imazamox ammonium, imazamox sodium, and fomisafen sodium. In their protonated forms, these formulations appear white, because their molecules only absorb light in the UV range. However, in their salt forms, imazamox ammonium and imazamox sodium methyl turn yellow, while fomisafen sodium methyl turns red as their absorption shifts into the visible spectrum. Now, as we understand the factors that impact the color stability of chromophore pesticide molecules, we can develop a strategy to stabilize the color in such formulations. The key strategies include pH control. Maintaining a stable pH is essential to prevent color changes in pH-sensitive active ingredients. Use buffering agents or design the formulation with inert components to keep the pH at a level where the molecule stays stable. Formulation optimization. Select compatible solvents, surfactants, and stabilizers to avoid unwanted reactions or pH shifts that could lead to color changes. Metal complexation assessment. Assess the risk of metal ions binding with active ingredients or inert components as this can affect stability, solubility, color, and efficacy. It's important to analyze the four metal ions and their potential to form complexes. Antioxidant incorporation. Include antioxidants to prevent oxidation, a common cause of color instability in active ingredients with conjugated double bonds. UV filters. Add UV filters to protect the formulation from UV degradation. These can be chemical filters, organic compounds, or physical filters, inorganic particles like zinc oxide or titanium dioxide, which absorb, reflect, or scatter UV radiation, preserving both the stability and color of the formulation. Packaging and storage. Use appropriate packaging that blocks light and air exposure to maintain stable color during storage. Stability testing. Perform long-term stability tests under various conditions like heat, light, and storage to identify any potential color issues and enhance formulation stability. Monitoring residual solvent effects. Check for residual solvents in technical ingredients as they can cause color shifts during storage and processing. Quality control measures. Implement strict quality control to ensure consistent production and color stability across all batches. Regular monitoring. Continuously track color stability throughout the product's shelf life with regular testing and make prompt adjustment if needed. By applying these strategies, formulations containing chromophore groups and conjugated double bonds will achieve better color stability, ensuring consistent product performance throughout their shelf life. Today, I'd like to wrap up our discussion about one of the fascinating challenges we face in pesticide formulations. As we have seen, something seemingly simple as a color shift often stems from complex molecular structures, like the chromophore systems we've discussed. Formulators encounter this issue frequently, but tracing it back to its molecular origins is not always easy. And this is just one example of the puzzles we solve in formulation work. Whether it's stability, process design, or other challenges, each case comes with its own unique factors. If you are dealing with any of these issues in your work, feel free to reach out. With my experience in this field, I am here to help find practical solutions. And remember, almost every formulation challenge has a solution. It's all about finding the right approach, and I am here to help you do that.